This is my fourth video about the best methods for converting acyl halides into ketones. This presentation is about the acylation of mostly ionic ketone enolates, for instance lithium, sodium or magnesium enolates, and of silyl enol ethers. Normal ketones have pKa's of about 26, and a complete deprotonation requires strong bases. Moreover, enolate formation is about 1,000,000 times slower than alcohol deprotonation and only proceeds with insoluble bases, such as sodium or sodium hydride, if the ketone is exceptionally acidic or in the presence of catalytic amounts of an alcohol. Stoichiometric enolate formation works best by adding the ketone to cold solutions of sodium amide, LDA, or sodium bis-trimethylsilyl amide, because the fast and complete deprotonation and the low temperature prevent any aldol condensation. Acylation of ketone enolates at carbon leads to the formation of a 1,3-diketone. These are much more acidic than simple ketones and will be immediately deprotonated by any starting enolate or excess base. Therefore, an excess of enolate or base is required for a complete conversion of the acyl halide. Enolates are ambident nucleophiles that can react with electrophiles at carbon or at oxygen. Oxygen acylation is a common side reaction of enolate acylations, but the resulting enol esters are still powerful electrophiles, able to react with the starting enolate to yield the expected 1,3-diketone. Some enol esters can also be isomerized to 1,3-diketones by nucleophilic catalysts, such as cyanide, or thermally, even in the gas phase. Esters in amides with alpha hydrogen are similarly acidic as ketones and can often be acylated under similar conditions as those of the following examples. The acylation of ketone enolates by acyl halides is a difficult reaction because enolates are not only strong nucleophiles but also strong bases and potent single electron donors. And acyl halides are also potential hydride and single electron acceptors, and may eliminate hydrogen halide and be converted into ketenes. Therefore, apart from the ready accessibility of the starting materials and reagents, there are no real advantages worth mentioning. Because of the high reactivity of the starting materials, these reactions must be optimized carefully, and reported procedures can be difficult to reproduce. Small details, such as the rate of addition or the precise concentrations, can have a severe impact on the outcome of these reactions. Then, mixtures of isomeric carbon and oxygen acylated ketones can be difficult to separate, and the yields of purified products are often low. 1,3-diketones are, furthermore, rather unstable compounds, which can be cleaved by strong nucleophiles, in particular if the diketone has no protons in position 2. Thus, the workup and isolation must be done carefully. This is an older organic synthesis example of the acylation of an acetoacetate. Because beta-keto esters are very acidic, they can be deprotonated with insoluble bases, such as sodium or sodium hydride. Furthermore, the salts of acetoacetates are only weak bases and nucleophiles, and therefore quite stable. The product in this instance is still more acidic than the starting acetoacetate, and too little base was used in this procedure. Less than 50% yield should have been obtained, but even organic synthesis yields are not always reliable. In this more recent example, the correct stoichiometry of reagents was used, that is, 2 equivalents of enolate for each equivalent of pivaluryl chloride. Because the sodium enolate had been isolated and freed from ammonia, and because pivaluryl chloride cannot form ketenes, a high yield of the diketone was obtained. This example shows how fast enolate acylation by such strong electrophiles as an acid chloride can be. Here it took only 2 minutes at 0 degrees Celsius for a complete conversion of the starting materials. The diketone wasn't isolated but converted immediately into a pyrazole by treatment with hydrazine. As in the previous example, the yield was high, probably also because of the essentially irreversible deprotonation of cyclohexanone by the strong base. In this example, a magnesium enolate was generated by copper-catalyzed conjugate addition of a methyl grignard reagent to an alpha-beta unsaturated ketone. This is again an example with incorrect stoichiometry. By adding one equivalent of acetyl chloride instead of only half, the reaction mixture turned neutral or acidic during the addition of the electrophile, and the overall outcome must have been highly dependent on the precise rate of acetyl chloride addition. The selectivity of reactions often depends strongly on the pH of the reaction mixture, and to obtain reproducible results, it is generally advisable to keep the pH more or less constant during additions and as the reaction proceeds, for instance by using an excess of base or acid. Anyway, in addition to a low yield of diketone, an enol acetate was also formed, and the overall result was apparently also impacted by the choice of solvent. This is an example of the acylation of a silyl enol ether. Unless the enol ether is converted into a more ionic enolate by treatment with fluoride, these acylations require activation of the acyl halide by an acid. In this case, one equivalent of zinc chloride was used as Lewis acid, and a high yield of diketone was obtained after only 1 hour at 0 degrees Celsius. Instead of stoichiometric amounts of zinc chloride, in this more recent example only 5% of an ammonium triflate was used as catalyst. Again, a high yield of 1,3-diketone was obtained. As already mentioned, several side reactions can interfere with the acylation of ionic ketone enolates by acyl halides and decrease the attainable yield of 1,3-diketones. These include the formation of enol esters from the starting enolate or from the product. At elevated temperature and when using weak bases only, aldol additions and condensations may occur. Under such conditions, sensitive products may also be cleaved again. If a large excess of acyl chloride is used, the product may be acylated again, both at oxygen or at carbon. Then, if the acyl halide has an alpha hydrogen atom, ketenes may be formed as intermediates, which can give rise to unexpected byproducts. Here are some further examples, also of investigations concerning the carbon versus oxygen selectivity and acid-catalyzed acylations. There are not too many examples in the literature because instead of using acyl halides, it is often more convenient to use less reactive acylating reagents for the acylation of enolates, for instance esters, as in the Claisen condensation. Finally, here are a few references of the isomerization of enol esters to yield 1,3-diketones and of the acylation at carbon by acyl halides of ester and amide enolates.